Hi, welcome back to a discussion on magnetic fields in matter. Now, this will be the last lecture on this particular module. And in this small video, I'm going to discuss about a qualitative theory about ferromagnetism. And thereafter, we'll discuss about hysteresis. I think it is already known to you. You might have studied in your higher secondaries. And finally, the phase transition. Okay, so let us begin with the ferromagnetism. Okay, we have seen that this ferromagnetism is a phenomena shown by certain materials in which certain materials shows a magnetization even in the absence of the external magnetic field. Okay, so a ferromagnet shows magnetization even in the absence of external magnetic field H. So therefore, how we cannot write M is directly proportional to H in the case of ferromagnetism, because even if H is 0, M need not be 0. So M I cannot write it is proportional to H. M cannot be proportional to H. But however, the change in magnetization, okay, we can write the change in magnetization. This change in magnetization would be obviously proportional to the change in the external magnetic field. So if you increase the external field, or if you decrease the external field, correspondingly there will be change in the magnetization. Now this change in magnetization, we can write the above expression as an equation is equal to chi m. Now this chi m would be proportional to h. So chi m is a function of h into delta h. Okay, so the thing is, in case of ferromagnetic material, the magnetization would depending upon the history of h, how h increased or how h decreased. So it entirely depending upon the complete history of H. Okay. Now, what is the theory of this ferromagnetism? That is how this material shows this particular property. Now, this theory is based on one concept called domain. So, domain is the region inside the material which contains billions of the magnetic moment or spin magnetic moment aligned in one preferred direction. So domain is a collection of, sorry, domain is the collection of large number of spin magnetic moment aligned in one direction. Now, if you look at a ferromagnet, so a ferromagnet contain very large number of domains. Okay, so we can just draw a ferromagnet. Suppose this is a piece of ferromagnet. So this ferromagnet contain different domains. Let us suppose this would be one domain in which all magnetic moment, okay, let it be uh, aligned in this particular direction. Okay, one thing I forgot to mention, this ferromagnetism is based on spin magnetic moment. There are two magnetic moment for atom. One is spin magnetic moment and other one is orbital magnetic moment. The paramagnetism is based on spin magnetic moment, whereas diamagnetism is based on orbital magnetic moment. And ferromagnetism is again based on spin magnetic moment, not on orbital magnetic moment. Okay, so the collection of large number of spin magnetic moment aligned in one direction is called domain. So this is one domain. So inside a material, we'll have a large number of domains. So this can be another domain. So here spin magnetic moment is aligned in towards right direction. So if you zoom a ferromagnet, we can see this kind of images. So if you have electron microscope and all, okay, so you can get such information. Now this may be along this direction. So a particularly a ferromagnet would be like this. Because this is just a qualitative picture. Okay, so it's domain 1, domain 2, domain 3, and there will be very large number of domains inside a small piece of ferromagnet. Okay, now this is the orientation of different domain in the absence of external field. So if H is 0, now if we apply the H in some direction, what will happen? So if you apply the external field, then what would happen is one particular domain, the area of one particular domain increases. So here, almost all domains will have the same area. But if you apply the external field, the area of one particular domain increases. Okay, so I will just draw once again the same picture. And let us we have the external field towards right. So if you apply the external field towards right, what would happen is the domain which in which spin magnetic moment has a direction in the direction of the applied field, its area increases. There is other domain, the other spin magnetic moment will try to align in the direction of the applied field. So the area of these two domains, okay, I can better write numbers. So number 1, 2, 3. The domain number 2, the area of domain number 2 increases, and the area of domain number 1 and 3 decreases. Okay, let this is domain 1, and let this be domain 3, and domain 2 increased. So the most of the area now contained with domain 2. So earlier, all three domains have the almost same area, and the total magnetic moment was 0, and total magnetization was 0. Here, the total magnetization would be non-zero. Okay, so hence this material will show a non-zero magnetization, and it will act as a magnet. Okay, so this is a situation. So the domain of a certain domain, its area increases, the other domain area decreases. Now, what will happen if you remove the magnetization? Sorry, if you remove the external field. Now, once you remove the external field, this material will not come back to its original configuration, because this process is a non-reversible process, irreversible process. Okay, so this process, we can say that it is an irreversible. Since it is an irreversible process, if you just remove the external field, it will not come back to its original configuration. So if you remove the field, so better I will draw it in next page. So what would happen if you remove H? So if you remove H, and then usually what happens is some of the magnetic moment will become random. So some of the spin magnetic moment in the domain two will come back to the orientation of domain one, and some will come back to the orientation of number three. And the area of one and three slightly increases, but it will not come back to the original contraction as we have seen earlier. Okay, so the one may be slightly greater, and 3 would be like this, and 2 will again dominate. Okay, so if you remove the H field, then the system does not go back to its original configuration, and it will have some residual magnetization. So magnetization would be non-zero, and again here H is zero. The external field is zero, but the magnetization is non-zero, and this material can act as a permanent magnet. Because now this material can produce its own magnetic field, so it acts as a permanent magnet. So this is the very qualitative theory about the ferromagnetism. It is not a very detailed theory. For detailed theory, we have to know the quantum mechanics, because that clearly explain the physics at the microscopic world. Okay, but for the time being, this gives some idea about how the ferromagnetism occurs. That is how a material shows the magnetization even in the absence of the external magnetic field. So that this theory, this domain theory, gives some idea about the ferromagnetism. So that is what we want. Okay. Now the next topic we want to discuss is the hysteresis. Okay. So if you take a ferromagnet, if you take some piece of ferromagnet, suppose its magnetization zero initially, and we have kept this ferromagnet inside a solenoid. Okay, now we can control the current in the solenoid. So if you increase the current in the solenoid, obviously the inside the solenoid will get a magnetic field. So your material would be subjected to external magnetic field, then magnetization increases. Okay, so now if you plot a graph between the current that you applied and the magnetization, see if the current is zero, the magnetization would be zero, and if you increase the current, the magnetization would also increase, and it will not increase continuously. After some point the magnetization saturates, because we have seen that in the previous topic, if you increase the H, the domain of the area of one domain increases, but there will be some limit. It cannot be increased continuously. It cannot be increased infinitely. Okay, so there will be some limit for the increase of one particular domain. So it would stop the magnetization. The increase of magnetization would stop after certain the H field. So when you are going to very high H field, the magnetization would become almost constant. So this if you increase I, you are increasing H. Okay, so after some point the H would become a constant. Okay, now what would happen if you decrease current? So right now we are increase the current and it reaches the maximum, which is saturated here. Now if you decrease the current, then this graph will not go back to the original pattern.